All right, today we're diving into something that's all around us, but we barely ever think about it. It's the hidden science that literally holds our world together. I'm talking about the unsung hero of construction, reinforced concrete. Let's get into it.
I mean, it's a good question, isn't it? You look at these massive buildings, these huge bridges, and they just seem so permanent. But how? What's the secret sauce? What keeps this stuff, which we all kind of know is brittle, from just snapping under all that pressure?
Well, it all starts with this weird contradiction. See, concrete has a superpower. It's a champion at being squeezed. You can put immense weight on top of it, that's called compressive strength, and it's totally fine. But it has a kryptonite. The second you try to pull it apart, apply what engineers call tensile force, it's terrible. It just cracks and fails.
So, you've got this material with a massive flaw. How on earth do you build a skyscraper with it? Well, you find it the perfect partner. And we're not just talking about mixing stuff together. This is like a perfectly engineered team-up of total opposites.
And that is what we call reinforced concrete, or RCC. The idea is so simple, it's brilliant. You take steel bars, you've probably heard of them as rebar, and you put them right inside the concrete. So now the concrete does what it's great at, handling all the squeezing, and the steel, which is amazing at being pulled, handles all the stretching forces. Together, they become this incredible supermaterial.
But here's the real magic. The scientific reason this whole thing even works. It's all about this one little number. This is the coefficient of thermal expansion. What does that mean? It means when things get hot or cold, both concrete and steel grow and shrink at almost the exact same rate. Think about that. If they didn't, they'd literally rip each other to shreds from the inside. This is like the secret handshake of the materials world.
Okay, so you can't just, chuck some steel into wet concrete and call it a day. The way engineers design these things is incredibly precise. And that thinking has really changed over the years.
The old way of doing things was called the working stress method. It was super cautious, kind of overcautious, really. It used these huge factors of safety, which meant you ended up with really thick, heavy, and kind of clunky structures. But today, we use something called the limit state method. It's much smarter. It looks at the ultimate strength of the materials and uses these more fine-tuned partial safety factors. The result? We get slimmer, much more economical buildings that are just as safe.
So, that's the big picture theory. But where it gets really interesting is how you apply it to all the different parts of a building. Every piece, a beam, a column, a floor slab, it's like its own little structural puzzle. Let's take a look at how engineers crack the code.
Let's start with a simple beam. You put weight on it in the middle, what happens? It wants to sag, right? But that simple sag is actually two different things happening at once. The top of the beam is getting squeezed together. That's our old friend, compression. But the bottom of the beam is getting stretched apart. And what's that? Yep, tension, concrete's ultimate weakness.
So how do we fix this? It's a 1-2 punch. First, we put the main steel bars, the long ones, right at the bottom of the beam, exactly where all that stretching is happening. Problem solved, right? Well, almost. There's another nasty force called shear that tries to create these diagonal cracks. To stop that, we add these vertical steel loops called stirrups. It's so cool. Every single piece of steel in there has a very specific job to do.
Now, what about the floors and ceilings? Those are called slabs, and they deal with similar forces. But how we design them all depends on their shape. Here's a simple rule of thumb. If the slab is long and skinny, like if its length is more than double its width, the load basically just goes in one direction. We call that a one-way slab. But if it's more of a square shape, supported on all four sides, the load spreads out in two directions. And you guessed it, that's a two-way slab.
Okay, let's talk columns. Their main job is just to get squeezed, which, as we know, concrete is great at. But there's a catch. Think about what happens if you squeeze a plastic straw really hard. It bows out to the side, right? The same thing can happen to the long steel bars inside the column. They can buckle outwards. So, to stop that, engineers wrap these smaller steel rings, called lateral ties, around the main bars to keep them from ever bowing out.
And what's holding this whole thing up? Way down at the bottom, you've got the footing. Think of it like the building's snowshoe. It's this big, wide base that takes all the weight from a skinny column and spreads it out over a huge area of soil, so the whole thing doesn't just sink.
But wait, there's one more crucial piece to this puzzle. All that steel is fantastic, but it's vulnerable. It can rust, so it needs a shield to protect it from water, air, everything. And what's the shield? It's the concrete itself.
This protective layer has a name, clear cover. It's simply the thickness of concrete covering the steel. And check this out.
The amount of cover changes depending on how exposed the part is. A floor slab safely inside a building only needs about 20 millimeters, but a footing sitting down in the damp soil, that needs a much thicker coat, about 50 millimeters, to make absolutely sure that steel never ever rusts.
All right, we've covered a ton of ground, from the basic theory to how it all works in practice. So, you think you've got it? Let's do a super quick quiz to find out. You ready?
Question 1. In an RCC beam, what's the primary job of those vertical loops we talked about? The stirrups? Are they there to resist A, bending, B, torsion, C, shear force, or D, compression? Think about it for a sec.
And the answer is C, shear force. That's right. The big bars at the bottom handle the bending, but the stirrups are there specifically to stop those diagonal cracks from shear.
Okay, next up. Picture a concrete slab. It's supported on all 4 edges, and its long side is 1.5 times its short side. So, is that designed as A, a one-way slab, or B, a two-way slab?
The answer is B. It's a two-way slab. Remember that simple rule? If the length divided by the width is 2 or less, it's a two-way. And 1.5 is definitely less than 2. Nicely done.
All right, last one. This is a bit more detailed. When we're using that modern limit state method, what are the partial safety factors we use? Is it A, 1.5 for concrete and 1.15 for steel, B, the other way around, or C, just 1.0 for both?
And the correct answer is A. It's 1.5 for concrete and 1.15 for steel. And there's a great reason for that. Steel is made in a factory, so its quality is super consistent. Concrete is mixed right there on the job site, so there's a bit more variability. That extra bit of safety factor just accounts for that uncertainty. Makes sense, right?
So there you have it, the incredible secret partnership between 2 totally different materials that makes our modern world possible. Seriously, the next time you're walking under a bridge or standing in a tall building, take a second, look around, because now you know the invisible engineering that's holding it all together. So my question for you is, what are you going to spot in the world around you today?